Alright, this little tutorial is on transition metal elements in ionic materials. Specifically, how do we know what Roman numeral to write for the transition metals, and how do we determine that using the formula? Okay, let's recall that transition metals are in groups 3 through 12. They have multiple oxidation states, many of them, because they can involve the unbonded d electrons in their shells. Remember, the d electrons and the s electrons in the next energy level are very close in energy, so they can swap in between the two. So for example, 4s electrons are very close in energy to 3d electrons. So sometimes the 3d electrons can be lost and involved in bonding. There are two other metals that exhibit this thing that aren't transition metals, and those are tin and lead. So when we name the transition metals in an ionic compound, we need to specify what the oxidation state is. Because again, some of these elements have multiple oxidation states, and therefore you don't know which oxidation state you're using. Groups 1, 2, and 13 metals only have one oxidation state. So you don't have to write the oxidation state because it's already given, or already known, and it doesn't change. Okay, let's look at two versions of iron oxide. So the first version, if we were to name it correctly, it would be iron 2, Roman numeral 2, oxide. And the second iron oxide, this is called rust also, is iron 3. 1, 2, 3, and the oxide. So they're both iron oxides, but one is iron 2 and one is iron 3. And you can see by looking at the chart here that they both have different chemical formulas, they both have different melt points, and they both have different densities. So they're different materials, even though they're all iron oxide. So we have to specify what iron oxide we're talking about. And in order to do that, since iron is a transition metal and can have multiple oxidation states, we need to tell you what that is. And the way we do that is with Roman numerals. So in the case of iron 2 oxide, the iron is +2. In the case of the iron 3 oxide, the iron is +3. So we're given the formula Fe2O3, and I want to know which of the iron oxides it is. Is it iron 2 or iron 3? Now, if we know from the previous slide, if you remember, that Fe2O3 is iron 3 oxide. But how did we get that? So the first thing we always do is I always write my formula, and I want to separate it into my cation and anion side. So I'm always looking for my second capital letter. Now this only works if it doesn't start with NH4. If it starts with NH4, then we don't have to worry about Roman numerals, because NH4 is not a cation that is it's not a cation that is a transition metal. It's a polyatomic cation. So we're going to draw a line right down between the second and first capital letter, and now we know which is my anion. So this is my anion, and this is my cation. Cations are always listed first in names and formulas. So now we're going to look up what is the Fe part and what is the O part. And we know that O equals oxygen from my periodic table. And so when we write the name, we're going to write oxide, because oxygen in the ion form is oxide. Now we know what Fe is. Fe is iron. So we look that up. So Fe from my periodic table represents iron. So we're going to write, so the name here is iron something oxide. And so let's put our Roman numeral here. We don't know what it is yet, but we're going to have to fill that in. Okay. So the way we can figure this out now is we're going to figure out what is the total charge on the anion side, because that's what we need to figure out first. So we have 3 oxygen ions. So we have 3 oxide ions. And each oxide ion is worth -2. So the math would be 3 oxide ions. Each one is worth -2. Remember, -2 because it's in group 16. And so the total charge on the anion side, is -6. Okay? Let me just erase that part right there and put that as a -6. So that's -6. So that means on this side we have -6, and then in the other side we need to have a +6. And why do we need a +6? Well, because when we add +6 and -6 together, we get 0, and we need 0 to balance the charge, right? The number of minuses has to equal the number of pluses. Okay, so we have +6 on this side, and that has to equal the number of iron atoms, and there are 2 of them. So 2 iron ions, times some number equals +6, and that number is +3. So it's +3, and therefore, since this is +3, we write the Roman numeral 3 here, because 3 means that it's a +3 charge. And there you have it. There is our way to get iron 3 oxide. Again, recap, we have to make sure that we have total charge on this side is -6, because we have 3 oxide ions right there, times each one is -2. That's from my periodic table, group 16. 3 times -2 is -6. So that's the total charge on the anion side. +6 has to be on this side. We have 2 iron atoms to contribute that +6, so each one is worth +3. And therefore we write 3 here. Okay, we're going to do a different way than just pure math. I'm going to try to show you something with more of a modeling approach or more of a graphical way of getting the same answer. So in this case, we're going to start exactly the same way. We're going to separate our cation from my anion side. So this is, again, my cation side, and this is my anion side. Now we're going to separate, we're going to say that this is iron. So Fe again equals iron. We looked that up on our periodic table. And then O equals oxygen or oxide, right? Okay, so now we're going to draw one box for every oxygen ion that we have, or every oxide ion we have. So let's do that. So we have, how many boxes do we need to draw? Well, there it is. It tells me right there, 3. I need to draw 3 boxes. So let's draw 3 boxes. So here's box 1, box 2, and box 3. Now, we're going to put something in the box, right? We need to put something in the box that represents the oxygen. So now the box equals the oxide ion. And the oxide ion is always -2. So that's what it's going to represent. So we have to put a -2 in each box. Now, how do you get -2? Well, if you look on your periodic table, oxygen is in group 16, and we said that everything in group 16 is -2. It doesn't change. It's always -2. Okay, so now we're going to sum this up, and we get -6. Remember, the total here, the sum, is the total charge of your anions, right? The total charge of the anions. Now, on the other side, we're going to draw one large box to represent the same size magnitude of the charge. And that charge has to be +6. So this whole box, this box right here, represents +6 because it has to be equal in size to this box. 1, 2, 3. We have 3 boxes here, right? Each box is -2. Total is -6. We don't know how many boxes we have to here, but we do know we need a total of +6 for this total side. And so the big box represents the total charge on this side. So let's write that in. So this represents the total cation charge. All right, So now, that's the total charge, but what does each iron bring to the table? So it says here that we have two iron cations, or iron ions, in this total big box. So we're going to split the box in half because we have two. So now we need two box pieces. And there they are. So now, what number do I have to put in this box here and here? Has to be the same number to give me plus 6. And you can see that that's going to be a plus 3. All right. So now what do you got to write now? So this number right here, I'm going to circle it with yellow. This number here is your oxidation number, oxidation state of your iron. So now we're going to write the name. So we have iron. We look for the Roman numeral 3 because the oxide state is plus 3, and then we just write oxide. And there's your answer, right? You can see here how this matches up, right? Hopefully you can see that on this side I have a total of minus 6. This side represents a plus 6. Each iron brings in plus 3. That gives me the plus 6, so that's iron 3 oxide. Okay, we're going to do it again, and this time we're going to do the box again, but I'm going to quickly go through this. Again, we separate our cation from our anion. And the reason why I do that, again, is because I want to be able to do an accurate count for all of my charges and put the correct number of boxes. Okay, so now I'm going to look up what each one of these is. There's Ti and P. So I'm looking up Ti, and I'll find that on my periodic table it's titanium. And then I look up P, and that's phosphorus. But we don't care about the phosphorus, we want the phosphide, because it's going to be the ion form. So it's phosphide. And we know that the phosphide ion is always minus 3. Okay? That's the oxidation state of phosphorus, minus 3. All right, so now what we're going to do is draw our boxes. So it says here I have 4 of the phosphide ions. So I'm going to write 4 boxes. So box 1, box 2, box 3, and box 4. Then we're going to put a minus 3 in each box because that's what the charge is for each phosphide ion. And my total charge is minus 12. Remember, the total here that's the overall anion charge. So that's the total charge on the anion side. All right? And therefore we need a big box on this side to represent that total charge on this side. So this is the total cation charge. And remember, this is going to be plus 12. So whatever we write in this box here, whatever the numbers we put in this box, have to be plus 12 total. All right. So now we're not quite done, but we're getting very close. We're going to look on this side, and we're going to see that we have 3 titaniums that make up this total box. So we're going to separate the box into 3 equal pieces. And there they are. Now, in each piece, I have to write one number, the same number, that when we add them all together is plus 12. So what is that number? That number turns out to be plus 4. So now when we see the plus 4, now we know that the plus 4 is the oxidation state charge of the titanium ion. Okay? So now when we write our name now we have a spot that we can write everything out. So it's titanium again. We always write the main name, full name of the metal. Then we're going to separate it with this oxidation state, which is a Roman numeral, and 4 is represented by the Roman numeral 4, and then we write phosphide. And we are done. So in this last example, I'm going to do it both ways to show you that the same number gets both ways no matter which way you do it. And some people say, I like to do the math way because I don't have to worry about drawing a lot of boxes. And some people say, I like drawing the boxes and it helps me visualize what's going on. So whatever way works for you, that's the way you should stick with it. But I'm going to show you that both work. All right, so I'm going to go a little bit quicker here as far as getting to the start point. Remember, I'm just going to draw a line here. And remember, we already know that this is my anion side. And again, this is my cation side. And I'm just going to write that Mn equals manganese. You can look that up. I'm not going to. And then O equals oxide. Right? We already know it's oxygen, right? And the oxide. And then we also know that the oxide always has a -2 charge. But we don't know what the manganese is yet, right? So we're going to do the box way first, and then we're going to do the other way second. Okay, so the box way says, I'm looking here and I see that I need to write 7 boxes. And each box is going to represent one of these oxides and have a -2 in it. So here I'm going to draw my 7 boxes. 1 box, 2 box, 3 box, 4 box, 5 box, 6 box, 7 box. And that's what it's going to represent. The box is oxide. So this is this. And each box we're going to have -2, so let's do that. And I'm going a little fast here, right? You can, so therefore, and then we're going to sum it up and we get -14. So that, remember, this is the total anion charge. Now, on this side, we're going to draw the same size length box as all the boxes combined on this side. Sorry for my box down here, it kind of didn't. And then, so on this side, we need a +14. Because it's -14 on this side, so I need a +14 here. Now, I go back up to my formula, and I see that this is going to represent the total cation side, and I have 2 cations here, 2 Mns. All right, so I'm going to do that, and since I have 2, I'm going to divide my box into 2. Because each one represents a Mn. So remember, this is my total. Sorry, that was bad. Let's get rid of that. And so this is my total charge of my cation. And each box represents 1 Mn. So we can just put this here. This is an Mn, and this is an Mn, just to show you what they are. Remember, these green boxes are all the oxides. All right, so what number do I need to put in each box that when I sum them together gives me +14, and it has to be the same number, and that number is +7. So +7 + 7 is +14, right? And now I know that this is my oxidation state. Of Mn, manganese. So that's that. Okay, so now we know that's what. Now let's do it the other way. So this time I'm going to use blue for the math part on this side. And we said that there are 7 oxides. Each one is -2, so that's a -14. So -14 again. So this -14 would go down here, just like you did. And therefore, this side right? This side here has to be a plus 14. So we go up to back to here, and we look how many MNs we have. So again, we have 2 MNs times some number equals plus 14. And then if you do the math here, you get plus 7. So again, this plus 7 is the same number as that, and that's the oxidation state. So if we were to write the name now, I'm going to write the name right here. We would go manganese, and then it's 7, so it's a VII, and then I'm going to put down here the oxide, and that would be the name. So it works both ways, right? And it shows you that you both get the same oxidation number, 7 or 7, depending on, doesn't matter which way you do it, box way or just straight math way. So hopefully this was helpful, and you have another technique you can use if you're not doing well with the math way. You can do the box way.